Good morning. My name is Mackenzie Vedas, and for my Lab Experiment 7, Equilibrium Le Chatelier's Principle, I will be going through Part B, Dissociation of Acetic Acid, and Part D, Copper Complex. So starting with Part B, the dissociation of acetic acid, we're going to look at the addition of sodium acetate, which is slightly alkaline, and the addition of sodium hydroxide, which is a strong base, to the original solution, which is acetic acid. So looking at the original equilibrium equation, we have our acetic acid over here, and we see that it breaks up into the acetate ion and H3O+. Now, this is just kind of a brief note. H plus doesn't really exist. It's represented by H3O+. So you can easily see when this hydrogen breaks off, it bonds with the water to form this. So looking at acetic acid with the addition of methyl orange is just an indicator to show how acidic or basic something is. So since acetic acid is a weak acid, it'll have more of a reddish color to it, so that means its pH is below 4.4. So starting with this somewhat weak acid, we are going to add sodium acetate, which is slightly alkaline, so that causes the color to become more of an orange. So here we see that there is a shift to the left because the ion is added to the product side, so the equilibrium has to shift to the left to maintain its balance. Next, we have this addition of sodium hydroxide, so we would have taken a new test tube with the acetic acid and methyl orange, and we would have added sodium hydroxide, which again is a strong base, and the hydroxide would cause it to become more basic, hence the yellow color. So that means that it has a pH above 6.2, and the pH is above 6.2 because the hydroxide ion bonds with the H plus ion on the product side, which is causing a shift to the right. Okay, so next, I don't have another set of test tubes, so I am using a drawing of the copper complexes and what the test tubes look like. So starting off, we have our copper complex equilibrium reaction, which is shown here on the bottom. And there's a lot going on here. So we see that the H2O wants to loosely connect to the copper. And we also see that we have the NH3, which is off to the side. And then we'll see that there's a switch between where the NH3 is located and where the water is located. So starting off, we have it's represented better in a picture, but this blue color is meant to be a light, almost clear blue. And that's just the copper sulfate. And when we add the NH4OH, we see a shift. This is what it would look like. We see a shift to the right because it's making more copper hydrate. Now, since it was originally a light blue solution, it becomes a more darker blue solution right there. So that's what indicates the shift in color. Then we would take what we had with the NH4OH, instead of getting a new test tube like we did in Part B, we would just continue to add to it. So we're taking now this dark blue solution, almost a royal blue color, and then we're adding HCl to it. So HCl is a strong acid, and it's hydrochloric acid. And what this would look like is we would see that it would form the copper chloride, and it shifts the equilibrium to the right. So when we see this in a test tube, it's got like a turbidity, it's kind of cloudy, and it forms the compound the CuCl4 2-, and that's what's causing the equilibrium to shift. Thank you for watching and have a great week.